Okay, hello everyone again. We're back with the optics equation sheet. So in the previous video over here, I went through this equation sheet very quickly and kind of just off of my memory, off of what I've learned and what I've done in class and stuff, circled equations that I know the name of and maybe I can see one or two times in the book and I kind of have a bit of familiarity of what they're talking about. I circled those guys in green. Equations that I don't know anything about or that I'm a little bit uncomfortable about, I circled in red. As you see, I've made some changes over here in pink, in this pink font here, and I wrote, where is this? Question mark, question mark. And I added a couple of notes for myself. So you could see a couple of these equations. So for example, this one here, it was circled in red. I wrote here equation 36.8 in pink. This one here was circled in red. I wrote some pink notes over here. This one I actually did not write any notes about. Same thing with this one and this one and this one. So this, and this are the only red equations I found no information on. So I'm going to start off with those, but I just want to give you guys a big overview. I have this equation here, which I wrote some pink stuff about. This one over here, I wrote a pink line. And this information, this was also red, red with pink notes, pink notes, pink notes. There's another red equation here with pink notes. This one here, I wrote some questions, but like I said before, no pink notes. And over here, I have a green equation, but I wrote, what is this? And I wrote another pink note. So these pink notes are me quickly looking through the chapters of the textbook to locate where these equations are at. So today, my hope is to go through these guys with you in real time and learn what these equations are doing. It's going to be very surface level. I'm not going to do any problems with this. As you saw in the first equation sheet video, I didn't solve any problems with these equations, but I just kind of named them or I kind of explained what they do. If you're able to do that for everything on this page, then you can kind of dive in and start solving problems with each of these. So you kind of want to do one sweep through of this entire equation sheet. Make sure you're able to circle everything in green. Once you're done that, you can erase all of this or just print a new equation sheet and look at each of these equations and be like, okay, do I have at the forefront of my mind one problem or two problems that use this equation that I can kind of relate some kind of problem solving technique to? If you could do that for each of these equations and you can explain what each of these equations means and what it can do, and you at least know its name so you can do further research on it, you're at a good stage. I know the midterm is in a couple days here, so I hope this is helpful. It's not going to be too like problem solving intensive. It's just going to be surface level information. So, like I said, I have four equations here. This one, this one, this one, and this one that I did not find anywhere in the chapters. We have four chapters that we have to do for this midterm. I went through every equation in all of those chapters twice, forward and backward, and I couldn't find these equations anywhere. So what I suspect is the case with these four equations is that the professor that you are studying this course with has given you guys some personal slideshow notes. Perhaps these equations are in the slides. I do remember the first week the professor did some kind of stuff related to waves. I think this equation is somewhere there. These two equations are related to this, and this last equation here is related to chapter 3738. And how I know this is I literally plugged all of these into ChatGPT and I just said, hey, I'm confused about this. Please explain it to me. So I'll show you guys this over here. And that's pretty much all I'm going to say for each of these equations. I don't really want to spend that much time on it because this video is going to be immense if I talk about each equation. So I'm going to just erase this for this first equation. Boom, erase this, erase this. And I will pull out my green color again. Let's hope it's this green color. And I will circle this like that. And I learned from ChatGPT that this is standing wave equation. So is this important? Maybe not too much. I haven't seen too many standing wave problems in this class, but it's good to know what it means. Maybe you could search up on YouTube standing wave equation, check Wikipedia, ask ChatGPT a couple questions. I'll say right now that this is the equation that gives you the y-axis of the wave. So normally if you plot it here, maybe as a function of time. So here you have y as a function of time. Since it's a standing wave, it's also a function of position x. So you could have another axis here that's x. I don't know if we can go all the way there, but basically you have some kind of function like this. It's oscillating as a function of time and as a function of position. It depends on k over here, which we saw was the wave number. It depends on omega, which is like the angular frequency. It has some kind of amplitude here. So standing wave equation. That's all I will say about that. Now I'm going to erase this equation here and this equation here. And I'm going to circle or box these guys here in green. And actually, let me do this one here as well. So maybe I will do something like this. Combine both of these because these are natural frequencies of standing waves. You can see this on ChatGPT as well here. Something related to harmonics. Again, I haven't really seen a problem related to this, but maybe you could search up something related to standing wave frequencies on YouTube. Normally what I think about is like a guitar string with a specific length. So this capital L over here. And when you flick it, it forms a standing wave, right? Because it's pinned at the ends. And these are the natural frequencies. So that's why this N over here increases in integers. You could have different frequencies that are natural to the string. In this one here, I guess if you have 4 times L, there is only odd natural frequencies. Again, I'm not too sure where you could see this in a problem. I'm just kind of sharing with you guys what I learned from ChatGPT. So those are 3 equations there related to standing waves. And again, haven't seen them anywhere in the book. Please let me know if you find them anywhere from chapter 35 to chapter 38. I would be glad to read upon that. And like I said before, I think it might be somewhere in the professor's notes. Now, this equation here, I wrote what is R. Let me box this in green. And I will erase this and erase this. And I will write, again, I'm not too sure about this because I just kind of read upon it, like about it a little bit surface level. But I do know this R stands for resolving power of some optical device. So I don't know, maybe some in chapter 38 you talk about gratings and stuff like that. So basically right here we have 2 different wavelengths, wavelength 1 and wavelength 2. When you add them together and divide by 2, on the top you get the average wavelength that your optical device is observing. On the bottom you have a difference of the same wavelengths. So this difference and this kind of average on the top is telling you like the minimum resolving power of your optical device if it can observe these kind of wavelengths here. So you plug in kind of like the smallest difference of wavelengths that your optical device can distinguish between. And here you take an average. This N and this M, I kind of forgot what it stands for. Let me pull up my ChatGPT thing here and peep what it says really quickly. Resolving power of an optical system such as a spectrometer or diffraction grating. Cool. In a diffraction grating, this is improved by increasing the number of grooves N, capital N, or using a higher diffraction order M. So N and M stand for diffraction grating and diffraction order. Again, not too sure where you might see this equation. I'm just greening it out here because I've seen it. I know that it means resolving power, and now I can Google search about it a bit more and do some problems with it. All right, so equation sheet looking a bit nicer. And those are the 4 equations that I couldn't find anything about in the textbook. Now we can kind of commence with each of the equations, and what I will do actually is I'm going to pull up the Light and Optics textbook right here on the side, the beginning, part 5, the humble beginnings, back when I read this and I didn't know what Huygens principle was. We've come a long way with this equation sheet. So what I will start with is literally just isolate an equation. So this one here, I average I0 cosine this thing. I wrote not sure, check 38.2, section 38.2, check equation 38.2 and 38.3. But then later in the book, I saw that this equation, the first time they introduced it, is 37.14. So there's a couple differences. This cosine squared equation, first of all, it appears right here. You could see equation 38.9. But if you check equation 38.2 and 38.3, they look very similar to this equation and this equation as well. But the first time they introduced this one is in 37.14. So I'm going to pull up my little bookmarks here, go to 37, and just swipe through here. Also, there were some corruptions in my textbook, so maybe that's why I'm missing some of the equations that I just went over. But anyway, we have somewhere over here, equation 37.14. Wait, did I miss it? I maybe did miss it. I did, my bad. Kind of zooming through this pretty quickly. Okay, here it is. Same exact equation. So that being said, I'm gonna erase this. I wrote over here chapter 38. And now that I found exactly where it is, I'm gonna erase this red text. And you know what? I'm gonna keep this pink text because it'll just kind of remind me like where I got this equation from originally. So I have this. I'm gonna put a little circle on it like that, oval, center it like that. Cool. I like seeing all that green. It's making some progress. But let's read a little bit about this. So what section is this in? Intensity distribution of the double slit interference pattern. Intensity distribution. So I actually haven't read this too much, but here I can see they do some derivation. They bring into play some kind of energy related stuff over here. They bring into play this phase difference thing. They do some kind of manipulation, and then they finally derive this equation. And let's read the paragraph just above this. It says, where I max is the maximum intensity on the screen, and the expression represents the time average, substituting the value of phi given by equation 37.10 into this expression gives this. Alternatively, because sine theta equals y over L for small values of theta, in figure 37.5, we can rewrite the equation as this for small angles. Okay, so you can read about the theory here if you want, but what I want to show you guys is that this I max tells you how to find this envelope over here of the Young double slit pattern. So you see that little light blue dotted line above all of these interference patterns. It changes as you go down. So n equals 10 over there. You can see that the light blue dotted line is almost flat, like it still has a gentle curve to it, but as you move up, the curve is a bit stronger and stronger. So we can read over here, for any value of n, the decrease in intensity in maxima to the left and right of the central maxima, indicated by the blue dashed arcs, is due to diffraction patterns from the individual slits, which are discussed in chapter 38. So this is chapter 37. They first introduced this. If you want to read more and do some problems, chapter 38, the next chapter after this one, is where they talk about intensity distribution. So just in general, that is that equation there. Should we go in order here? Maybe we should. So let's take a look at this equation over here. So I did draw a lot of red stuff here. I'm going to just erase all this red. Why no negatives? I'm going to remember that and just erase that there. Related to Young's experiment, okay, I will also erase this. And that equation, I do remember, it is somewhere up here. So I remember that, oh my bad. Here we introduce the Young double slit, which I circled as green last time. But then in the following chapter, so 37.3, this is what we just went through. There's another section here, change of phase due to reflection. So this section 37.4 is super important when it comes to the equation that we're about to circle green here. So if you're interested, take a look at this and read about what happens upon reflection, this phase change stuff that we've kept talking about. And then that leads, after this singular page, 37.4, it leads into interference of thin films, which is exactly what this equation over here is talking about. So I'm going to box that in like this. You can see I've actually wrote in pink over here 37.5, which is exactly the section we're in, specifically equation 37.17, which is this equation over here. See, it looks pretty familiar. And we have m equals 0, 1, 2, so on and so forth. So why I wrote why no negatives is because I compared this Young double slit equation to this thin film equation, and you can see for the Young double slit, you actually have m equals 0, m equals plus minus 1, m equals plus minus 2. But in this section, when you're talking about thin film interference, you only have 0 and the positive integers. That is the same for this following equation, which I will also actually erase the red from right now, and I will circle it or box it over here in green. It's a bit easier to do boxes. And the reason I'm boxing it is because you can see that equation is the one located right over here. Okay, so now that we've boxed those and we have kind of the general idea of where it is, you can read about this section, but let's just take a look at, let's read maybe this over here. Or maybe let's read from here. In general, the condition for constructive interference in thin films is, and then they give you this general equation. By the way, this general equation is nowhere in the equation sheet, but you can see if you use this equation and you plug in this from above, you can basically derive this equation and this equation, which are both in the equation sheet. So this condition takes into account two factors. One, the difference in path length for the two rays, the term m lambda subscript n, and two, the 180-degree phase change upon reflection, the term 1/2 lambda subscript n. Because lambda subscript n equals lambda divided by n, we can write equation 37.16 as the following, which is for constructive interference, right? If the extra distance 2t traveled by ray 2 corresponds to a multiple of lambda subscript n, the two waves combine out of phase and the result is destructive interference. The general equation for destructive interference in thin films is this one. So I'm actually going to write this over here. I will literally write destructive interference. And for the other one, so that is for that one there, for the other one over here, I will write constructive interference. And for both of these, where I put this pink stuff, I will just write thin films, section 37.5. So why is this important? Well, take a look at this equation here and this equation here. I told you guys before that it looks super similar to this equation here and this equation here. Why is that the case? Because we have an m lambda over here and an m lambda over here and an m plus a half lambda over here and an m plus a half lambda over here. The only difference is this d sine theta, which is here and here for the Young double slit experiments, is switched for 2nt, which is the case here with the thin films. So typically they use the letter T for the thickness of the thin film, and they use the letter N for the refractive index of the thin film. And the reason I wrote constructive interference here is to distinguish it between the destructive interference over here. So remember, destructive interference of light leads to dark fringes. So you could see the m plus a half is actually the destructive interference for Young's double slit experiment. But the m plus a half is actually the constructive bright fringe equation for the thin films. It's almost inversed a little bit. Similarly, the bright fringe equation for the Young double slit is only this m lambda, and the m lambda equation here for the thin film is actually the destructive dark fringe interference pattern. So it's very good to know this in the exam. You have to distinguish between Young double slit interference compared to thin film interference, and you have to further distinguish between constructive interference and destructive interference. By the way, looking at this now, I'm noticing I have two different shades of green, which is super annoying, but Anyway, we're going to keep moving on with the shade of green I have over here. And by the way, one other thing I wanted to share about this is if you look at this picture over here, they actually show you interference in light reflected from a thin film is due to a combination of rays 1 and 2 reflected from the upper and lower surfaces of the film. And take a look at this word here, 180-degree phase change compared to no phase change. That's why I told you guys that this chapter, or this section here, 37.4 before, is a bit important to read through. If you don't understand this thin film interference, take a look at 37.4. That being said, once you're comfortable with this, there's a couple of problems here. So take a look at this problem. This is Newton's rings. You could read a bit about problems related to that. But there's also some problems here related to interference in a soap film. So a soap bubble is something like this. Sometimes you see interference of light related to the soap film. The soap is a thin film, so you can apply this thin film interference equation to figure out some kind of problems. Take a look at this example over here and see if it makes sense to you. And also there's another one here related to non-reflective coatings of solar cells. These are just the examples done in the book. I don't want to do them right now because the goal of this video is the equation sheet. So that being said, we are good with those equations. Equation sheet is looking about 60-75% green. And if we're okay with that, I'm going to move forward to, let's take a look. Let's go to this equation. So I wrote 36.8 because this equation looks very similar to the mirror equation. So this one, we can go back to, let me zoom all the way through chapter 37. And I said the equation was 36.8, so kind of earlier in the chapter, 36.9. Here it is, 36.8. So this equation here, you can see looks exactly like this equation here. N1 over P plus N2 over Q equals N2 minus N1 over R. So since that looks good, I'm going to erase this little red stuff over here, pull out my green, and box this guy in. Just because I've boxed it in doesn't mean I know what the equation is. So let's just read really quickly. It says, relation between object and image distance for a refracting surface. And you can read just a little bit, you can go just a little up and you see here 36.3 images formed by refraction. I actually haven't read this on the channel. I was thinking of doing a slower read through, but I don't really have time to release all of that before the exam. So this equation sheet video I think is a little bit more important. So you can see when you talk about refraction, like lenses or droplets of water, stuff like that, like for example, magnifying lens or something like this, you can develop this equation and boom, you get something very similar to the mirror and lens equation, except you have these refractive indices. So let's read just right here, the section just before this to see kind of what they're talking about. For a fixed object distance P, the image distance Q is independent of the angle the ray makes with the axis. This result tells us that all paraxial rays focus at the same point I. Okay, that's not too important. I was trying to figure out which index of refraction is N1 and which is N2, but we can actually see it in this picture. So N1 is the index of refraction outside of the piece of glass where the object is placed. You can actually see that by this letter P and this index of refraction N1. N2 is the index of refraction of the glass or the droplet of water or whatever your medium that is doing the refracting. And Q over here is the distance of the image. And then, of course, you have the difference of the refractive indices here. So again, just because we read about this a little bit in the book doesn't mean we're comfortable with doing problems. The equation sheet is just to kind of get you a bit comfortable with what the equation is actually talking about. And then you can scroll down here and see maybe you can check some of these examples here and see if you use the equation. Actually, this one, it looks like we used that equation right here. There's a couple more problems here. So that being said, I'm going to move on from this into perhaps this equation here. I actually wrote, this is the Lensmaker's equation, 36.15. So the same chapter, that's why I'm kind of skipping this and this and just jumping directly down to this one. So let's slide a little bit more and take a look at where the Lensmaker's equation is. And you can actually see they kind of start from this previous equation that we just figured out, this one right here, and they derive a little bit until they finally get to the Lensmaker's equation, which is exactly the one we're looking for. So we have 1 over f on the left side of the equality. On the right side, we have brackets n minus 1, brackets 1 over r1 minus 1 over r2. Cool. Let me erase this, pull out my green. Let's do a circle this time, or oval. And boom. Lensmaker's equation. I guess we could read here. Let's see what this is talking about. The focal length f of a thin lens is the image distance of a, sorry, that does not make sense. The focal length f of a thin lens is the image distance that corresponds to an infinite object distance, just as with mirrors. Maybe you haven't done a problem with that, but there's a scenario where if you place an object at the focal point, the image forms at infinity because the light rays are parallel and they never converge. Anyway, letting P approach infinity and Q approach F in equation 36.14, which is the one just above, we see that the inverse of the focal length for a thin lens is this, the Lensmaker's equation. This relationship is called the Lensmaker's equation because it can be used to determine the values R1 and R2 needed for a given index of refraction and a desired focal length. Interesting. So in this YouTube channel, in this class, I haven't really done too many problems related to this equation. So I'm not sure what R1 and R2 actually mean. There's this picture over here which says R1 and R2. They point to them here. But what does that mean? Does that mean radius of the lens, or I'm not too sure. So it would be good to do a problem. And I haven't actually seen any problems here. This one here uses the actual just lens and mirror equation. So take a look at some problems with the Lensmaker's equation, or just, kind of try to understand which problems would use this equation as opposed to the classic mirror and lens equation that we have here. All right, nice. Let's take a big overview. So we have 4 equations left. I guess we can go, because all of them seem to be in chapter 38. Yep, it looks like all of them are in chapter 38. So we're going to sweep through. This is chapter 36. So we're going to go all the way, boom, 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 through the whole textbook to chapter 38, diffraction patterns and polarization. I haven't really read this chapter too much on this channel. I've read just kind of bits and pieces. So if that is your scenario as well, and you feel uncomfortable with this chapter, I would say read about it quite a lot. But we're going to sweep through here until we get to this equation, which actually ends up being the first one on our equation sheet. Condition for destructive interference for a single slit. Now take a look at this. We have this equation over here, sine theta, and we have sine theta dark in equation 38.1. Here we have n, and the equation 38.1, they actually use m here. But the equation is the exact same. We just replace one letter for another. Otherwise, the math is all the same. We have a lambda here, we have an a over here, and we can see that this little index variable n, which is called m in the textbook, it takes on all the positive and negative integers, excluding 0. Cool, and this is telling you that it is interference, destructive interference specifically for a single slit. So just like how we saw the double slit interference, there's waves coming here from Young's double slit and it creates like bright fringes on a screen and dark fringes over here. There is also kind of a similar effect with just a single slit. So let's say there's plane waves coming here. They pass through this and they come out kind of as wavelets because of Huygens principle. So it creates some kind of pattern. And I guess this, you could use it the same sort of manner. You could read up on this a little bit more if you go here. So over here, they show you a classic viewing screen and kind of the same setup as Young's double slit, except you could see the interference pattern is a bit different. So the equation, of course, is a bit different. Diffraction patterns from narrow slits. And they also show you something over here, which looks pretty interesting. Anyway, there is a problem here, example 38, which we can do, but definitely not in this video. This is the equation sheet video. So I'm going to erase that. I'm going to erase this. I wrote here similar to Young's experiment. It is true. It is pretty much Young's experiment with just one slit. And then I'm going to pull out my green use a oval right here. And boom. So we are okay with that. Cool. We're going to keep going forward and take a look at this. This equation looks kind of familiar, and I actually wrote over here, not sure, check section 38.2, check equation 38.2 and 38.3. And over here, you can see equation 38.2. The reason I wrote that is because I saw I equals I and then something complicated over here. So this is not the same equation as the one we saw here, and it is not the same equation as the one you see here, but it is pretty similar. It is an intensity equation specifically for the single slit diffraction pattern, and they actually name it, they call it Fraunhofer diffraction pattern. So I'm just outlining that. I've actually outlined something else in pink over here, if you can see. Combination of thin lenses, section 36.4. So I just wrote this little thing here for myself because I noticed this entire equation sheet, it includes a lot, but there is some things it doesn't include. So one thing it doesn't include is some equation for the combination of thin lenses. When you combine thin lenses, you have magnification that looks like M total is equal to magnification 1 times magnification 2. F total, so focal point of the total, is equal to, some combination of focal points. So this is something to go over if you have a bit of extra time. You can't learn everything on all of these 4 chapters. It's very difficult, especially in like a short amount of time like this. But if you can take note of something that's missing from here, just to complete your knowledge, it is good to do. Similarly, this Fraunhofer diffraction pattern, I have not seen it in the equation sheet, but I have seen something similar to interference patterns here. So anyway, just keep that in mind. Maybe you can Google search Fraunhofer diffraction pattern. What does that mean? What does it do? Yeah, it might be kind of interesting for you guys to see. Also, there's these cool pictures that show you, I guess, a Fraunhofer diffraction pattern, which might kind of spark your interest. Anyway, it is not on the equation sheet, so we're going to keep moving through. And we are going to get somewhere over here to the limiting angle of resolution for a circular aperture, equation 38.6, which is exactly this one here. Theta minimum equals 1.22 times lambda divided by capital D. So I wrote resolution as a guess. I wrote aperture. I wrote wave interference. These were all pretty solid guesses from my first kind of run through of the equation sheet. So it's very good to do this. Check again my first equation sheet video to see kind of how I went through this. But I'm going to put a green circle around this because I now know what it's called. I'll just write over here limiting resolution, and it is for a circle aperture. Just write it like that. I always have the equation and the section over here if I forget anything. But what does this mean? Well, resolution kind of means, when I think of resolution, I think of blurry compared to crystal clear videos. So over here, you can actually see there is, let's read over here at the top. The two sources are closer together such that the angular separation satisfies Rayleigh criterion and the patterns are just resolved. So they use the word resolved and they say it's almost resolved. That's the central image over here. If we read this one over here, it says the sources are far apart and the patterns are well resolved. So now we can kind of understand what resolved means. It's like you can tell the difference between the two waves or diffraction patterns there. Let's read this final one here. It says the sources are so close together that the patterns are not resolved. So a bit of kind of definition of what the word resolved means here. Of course, you can read up on this up here. We did see the word or Rayleigh's criterion. I don't know who Rayleigh is. Rayleigh's criterion is over here in bold, and it is under this section, resolution of single slit and circular aperture. So if you want, take a look at this, see what it's about. And here we have a resolution of the eye, which is a very interesting problem, which I'm assuming uses this equation here. Let's actually take a look. Boom. It is exactly the equation that you use. So you can see just by knowing the name of the equation, resolution, circular aperture, and they ask you for some question like boom, 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 light of blank enters the human eye, pupil diameter from person to person varies, Estimate the limiting angle of resolution for this eye, assuming the resolution is limited by diffraction. That sounds crazy if you have no idea what you're doing, or if you have no idea what the chapter is about. But if you just know the name of a single equation, I'm sure with a bit of pressure and a bit of ingenuity, you can pull through and you can solve a problem by just plugging some numbers in. And also, resolution of the human eye is pretty pimp. If you can answer that, I'm sure it's a great icebreaker on a first date. So try that out. That being said, I'm not solving any of these problems today. I'm just moving through, trying to show you guys how I would, study for a test like this, how I would figure out what every equation is on the equation sheet. And like I said at the beginning of this video, you don't want to do this just once. Do this multiple times. After you circle everything green on the equation sheet, you want to go through each individual equation, try to solve 1 or 2 or 15 problems for each of them, and then you'll master physics, and you're going to have a great time, trust. So let's keep going through and find the final equation in this chapter. I think I said actually all of the equations are in this chapter, so we have 2 more equations here that should be in this chapter. Maybe I passed it. Oh, here we go. Malou's law. My boy Malou. Malou's law. His name is Malus, and then you say plural Malus, or like not plural, but like possessive or whatever. So anyway, we have this equation here. I is equal to I max cosine squared theta. Like I said before, this is kind of ringing a bell over here because we have an I, we have a cosine, we have some complicated stuff in the cosine. But you can see that's the same equation as this one here. And interestingly enough, in this case, we don't have anything complex inside the sine. We literally just have theta. So now that I found this equation, I'm going to erase my red, put a box around this, and I will actually just write Malus's law. Because if you have the person's name, you could straight up go to Wikipedia and type in Malou's law optics, and you can have the whole history, several problems, and an entire derivation of this equation just by knowing the name. Okay, so let's take a look very quickly what this is saying. So I'm gonna read from here all the way to like about here. Because the intensity of the transmitted beam varies as the square of its magnitude, we conclude that the intensity I of the polarized beam transmitted through the analyzer varies as, and then they cite Malou's law, where I max is the intensity of the polarized beam incident on the analyzer. This expression is known as Malou's law, and it applies to any 2 polarizing materials whose transmission axes are at an angle theta to each other. Very, very, very interesting. So let's actually take a look at these images here. You could see this first image. Let's just read what it says here. The transmitted light has maximum intensity when the transmission axes are aligned with each other. And you can see those 2 red arrows are pointing in the same direction on the right side of those circles. Let's take a look at this middle one over here. The transmitted light has lesser intensity when the transmission axes are at an angle of 45 degrees to each other. So the only thing that has changed is the left circle. The red arrow is a little bit up. It's like at a 45-degree angle. It's like at about, if the circle was a clock, it would be around where 2 o'clock is. But the right circle still has the red arrow at around 3 o'clock. And you can see the light in the middle of that little Venn diagram has darkened. Similarly, if we move the other circle so that the red arrow is completely at the top, it says the transmitted light intensity is a minimum when the transmission axes are perpendicular to each other. So what I would argue is, if you take Malou's law and put cosine squared, and inside of the cosine where the theta is, you put 90 degrees, you should get 0. Is that correct? Cosine of 0 is 0. Cosine squared of 0. Let me actually double check that with my calculator very quickly, so I'm not like kind of giving you guys incorrect stuff. So cosine of 0 equals 1. Hold up. Cosine of 0. Oh, I said cosine of 90 degrees. Let's make sure this is in degrees. Cosine of 90 is 0, and 0 squared is 0. So I max times 0 gives you intensity of 0, which makes sense. If you plug in cosine of 0, so the angle difference between these guys is 0 degrees, you get maximum intensity. All right, test that equation out with a couple of problems. Let's see if there's actually a couple problems here. Um, it doesn't look like it because I noticed that we're on to the final red equation. I think it's the final red equation actually. There's another kind of final like red text that I have to resolve here. But take a look at this. Brewster's law. We got some cool ass names here, man. We got Malus, Brewster. We got the Lensmaker's equation. Um, Definitely stuff that you can share with your friends and family, and they would actually be super interested in what you're saying. So take a look at that. But now since we found this, I'm gonna circle this in green. I will write here Brewster's law. I'm assuming Brewster is someone's name, someone's last name. And if we plug in Brewster's law into Wikipedia, we can figure out anything about this. So it says tangent theta p is equal to n1 over n2, or sorry, n2 over n1. That's exactly what this says. And actually, it tells you here in the equation sheet that tangent theta p is also equal to n. So why is this the case? Well, you could take a look at how they derive this. Take a look at this equation up here, n2 over n1 equals sine theta, sine 1, whatever. And maybe you can compare it to another equation you've seen here. So take a look at this one. Like I said in the first equation sheet, you can use this equation and this equation, combine them together, and you can derive this equation. And if you have this equation and you have this, notice that sine theta 2 over sine theta 1 equals v2 over v1, or is equal to n2 over n1, and all of that is equal to a constant. So that's where I'm assuming this little n is coming from. This little n is a constant, and it's just an extra thing given to you in the equation sheet in case it is helpful. So Brewster's law. I have no idea what Brewster's law is. Let's take a look at some of this picture here. I'm going to read figure 38.28. When unpolarized light is incident on a reflecting surface, the reflected and refracted beams are partially polarized. Interesting. B. So that's part A. Let's take a look at part A here. This is part A. And let's read here. The dots represent electric field oscillations parallel to the reflecting surface and perpendicular to the page. Wow, this is crazy. This actually links optics back to electricity and magnetism, which, in a standard university curriculum, you take E&M before you take optics and modern physics. So cool kind of progression, cool connection between two courses there. Let's read the second thing. The arrows represent electric field oscillations perpendicular to those represented by the dots. All right, I'm not sure what that means, but let's keep reading here. The reflected beam is completely polarized when the angle of incidence equals the polarizing angle theta p. Interesting. So this little p actually stands for polarizing angle. I will actually write over here theta p equals polarizing angle. Maybe it might be helpful, maybe it won't be, but I like theta p because I am relating this little theta p subscript to this little theta c. This was total internal reflection, and I remember that because I remember theta c stood for the critical angle. So in this case, this is the polarizing angle. I'm not sure if it's similar. The equations do look similar. You switch out a tangent for a sine, and they look pretty much identical. But let's keep reading here. We have polarizing angle, which satisfies the equation n2 over n1 equals tangent theta p. At this incident angle, the reflected and refracted rays are perpendicular to each other. Okay, so something related to polarized light, something related to refraction and reflection. Actually, here we go. It is in the subsection called polarization by reflection. So maybe there's a couple problems here that we can do related to that. It doesn't seem like it. Polarization by scattering. No, there's no problems in this. Maybe there's problems at the end of the book. But anyway, that completes my knowledge. Or actually, no. Give me a second. I have one other thing to share with you guys here before I end off the video, and it is this magnification equation. So if you remember the magnification equation here, we can relate it to image height, object height. We can also relate it to image position, object position, and we also have this n1 over n2. and I wrote, what does n1 over n2 do to m? And I wrote here 36.9. So I actually was able to find something that explained this to me. 36.9 is, so over here is actually the first time they introduce 36.2, the magnification equation. 36.9 is the first section on refraction. You could see over here, images formed up by refraction, and you can see over here, flat refracting surfaces, and they actually do some kind of derivation and they get this equation here. So Q is equal to negative N2 over N1 P. So basically, if you have no magnification due to P and Q, you just have kind of a flat refracting surface, you also get some kind of magnification, because of this problem here. So I will just erase this, and let me whip out my pink color here and just connect this over here. And now I can close the textbook. We can take a look at the equation sheet overall. So guys, take a look at this. In 2 videos and in a bit of my personal kind of digging through the book, technically all I did when I looked at this is I looked at all the equations I circled in red. There's a bunch of equations here that I circled in red. And I was like, where can I find these? I opened the textbook, I sweeped through, and I just wrote down some quick notes of like what I found here, 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 here. I didn't read anything. I actually just opened up right now, started recording, and I wanted to go through this with you guys. I did this in 2 videos. I know the exam is very quickly approaching. Please go through this, try to do it on your own, and when you have everything on this equation sheet green and you can cover every single equation here, you can say what it is, each of the symbols inside of it, what it's called, where it's coming from, which section of the chapter it's coming from. I know it's a lot of stuff, but as you'll see, the more you look at this stuff, the more comfortable you get with each of these. That being said, once you're at this stage, go through, and I would say start with whatever you feel most uncomfortable with. So personally, there are some problems with thin film. So this equation here and this equation here, they are both related to thin film interference. I actually wrote that right here. I feel more comfortable with the Young double slit equations than I do with the thin film equations. So off the bat, if I start studying, I would jump into some thin film problems. Secondly, Brewster's law, I have no idea really what it was doing. I kind of just read about it pretty quickly. And Malouz's law, this stuff about polarization, about intensities, this stuff here, I don't know anything about that. So I'm going to just dive into where I am really uncomfortable with, make sure all of that feels good for me. Once you start covering a lot of stuff, you can kind of jump, choose what you want to study. If you don't know, just start with the first equation and the first couple equations and go in order and move through in order. If you feel bored with these, start from the bottom and move this way. If you feel bored with those, pick an equation at random. Start with this middle row. Be like, today I'm going to figure out what all these equations do. I'm going to do 3 problems on each. And do that over and over. Try to do that as much as possible. Don't try to make studying such a big chore. So this is one reason why I like writing the names of the equations. This one, the Lensmaker's equation. Where did the Lensmaker's equation go? Is it this one here? Lensmaker's equation, Malouz's law, Brewster's law, Young double slit experiment, thin film interference. If you have these words at the forefront of your memory, you don't have to sit down and make a big chore of studying. You could literally hop on your phone, open ChatGPT, open YouTube, open Wikipedia, open Google, and type in Brewster's law. On YouTube, just watch a Brewster's law YouTube video and you will see this equation. If you don't see this equation, maybe take a look at some other videos, but open up Malouz's law, take a look at some problems, and just watch it. Like, have fun watching it. It shouldn't be that kind of challenging. It shouldn't be that daunting. Just try to reduce the energy that it takes for you guys to study. Also, as you're reading through the book, take notes of stuff that you haven't seen before. Take notes of problems that have interesting tricks that try to trick you. Specifically, I have seen a couple of problems here with the thin films. I'll actually post them on the screen right now. Maybe I'll do a problem on this if I have some time before the exam. These problems confused me. They have a trick. They try to finesse you. They try to trip you up and make you make the incorrect kind of pathway moving forward. So keep in mind those types of problems, because that's the whole point with exams. They try to trick you, because if they try to trick you and you avoid, you deviate from that trickery, then you really know what the fuck
Beep.
you're talking about. You can actually confidently stand on business, and you can 100%, when someone asks you about some equation here, you can be like, yeah, I know what this is. I've done 3 problems about it, and I can, confidently say, like, I'm okay with most of the problems. At the end of the day, nobody knows everything. Like, you're for sure going to get tripped up on something. It's very hard to get 100% on an exam, but you can try your best. And good luck, guys. Keep studying, stay hydrated. Let me know if you have any questions. Drop some comments on this YouTube video, and I'll try to post some more videos before the exam. Also, talk to some friends and some loved ones. Call some relatives and just be like, "Yo, how you doing?" De-stress a little bit. I know it's kind of a tough time, midterm season right now. Good luck with your other classes too, and let me know if you have any questions. I'm always here. Thank you guys for watching. Peace out.